Number sign authorization and identity, A. Number sign authorization and identity, a deep dive into RBAC OAUTH 2.0 OIDC and claims-based design. Introduction. When we talk about securing applications, we're really talking about two fundamental questions. Who are you and what are you allowed to do? The first question is authentication. The second is authorization. And while these concepts seem simple on the surface, building robust, scalable authorization systems is one of the hardest problems in distributed systems. In this guide, we're going to explore the evolution from simple role-based access control, or RBAC, to modern claims-based authorization. We'll dive deep into OAUT 2.0 and OpenID Connect, understand how tokens work under the hood, and see how these patterns play out in real-world cloud-native applications. By the end, you'll understand not just what these technologies are, but why they exist and when to use each one. The limits of traditional RBAC. Let's start with RBAC because it's where most authorization stories begin. Role-based access control is exactly what it sounds like. You assign users to roles, and roles have permissions. A user might be an admin or a viewer or an editor, and each role can perform certain actions. RBAC is intuitive. It's easy to explain to stakeholders. If someone asks, "Can Alice delete this resource?" you check if Alice has a role that allows deletion. Simple. But RBAC breaks down fast in real-world scenarios. Imagine you're building a multi-tenant SaaS platform. Alice might be an admin in Company A, but just a viewer in Company B. Already, your simple role model is becoming complicated. You need to track role assignments per tenant. Your authorization check now needs context. Which tenant is Alice operating in right now? Or consider time-based restrictions. Maybe Alice should only have admin privileges during business hours. Or geographic restrictions. Alice can access data from European servers, but not American ones due to data residency laws. Or attribute-based rules. Alice can approve expenses up to $10,000, but anything above that needs a director. Suddenly, RBAC feels rigid. You find yourself creating dozens of hyper-specific roles. Europe admin, business hours editor, limited approver. Your role hierarchy becomes a tangled mess. Authorization logic spreads across your codebase because roles alone can't express the business rules you need. This is where claims-based authorization enters the picture. Claims-based identity, a flexible foundation. Instead of thinking about what role a user has, claims-based systems think about what attributes or statements are true about a user. A claim is simply a piece of information. This user's email is alice@company.com. This user works in the finance department. This user is over 8 years old. This user's employee ID is 12345. When Alice logs in, she gets a token containing her claims. These claims are assertions about her identity and attributes. Your application receives this token and makes authorization decisions based on the claims inside. The power of claims is flexibility. Instead of hard coding, if user has admin role, allow access, you write policies. If user has claim department equals finance. And claim approval, limit is greater than or equal to requested amount, allow access. You can combine claims in arbitrarily complex ways without creating new roles. Claims are also composable. Different systems can add different claims. Your identity provider might add basic claims like email and name. Your HR system might add department and manager. Your application might add application-specific claims like subscription tier or feature flags. All these claims flow together in the user's token. This brings us to the question, how do we get these tokens? How does authentication actually work in modern systems? That's where OAUTH and OpenID Connect come in. OAuth 2.0, the authorization framework. Here's a critical point that confuses many developers. OAuth 2.0 is not an authentication protocol. OAuth is an authorization framework. It answers the question, what is this user allowed to do, not who is this user? The classic OAuth scenario is delegation. You want to let a third-party application access your Google Drive files without giving that application your Google password. OAuth solves this by introducing access tokens. Here's how it works. You're using a photo printing service. The service wants to access your Google Drive photos. Instead of asking for your Google credentials, the photo service redirects you to Google. You log in to Google directly, and Google shows you a consent screen. Photo printing service wants to read your Google Drive files. Allow? You click Allow. Google then gives the photo service an access token. This token is a credential that proves Google has authorized the photo service to access your files. The token is scoped. It only grants access to read Drive files, not send emails or delete your account. And it's time-limited. It expires after an hour or a day. The photo service sends this access token with every request to the Google Drive API. Google's API validates the token and allows the request. At no point did the photo service see your password. You never had to trust them with your credentials. This is OAuth's big idea, delegated authorization via tokens. Now, let's talk about the players in OAuth. There are 4 roles. The resource owner is you, the user. The resource server is the API holding your data, like Google Drive. The client is the third-party application, like the photo service. And the authorization server is the system that issues tokens, like Google's OAuth service. The flow we just described is called the authorization code flow, and it's the most secure flow for applications that can keep secrets. Here's the detailed sequence. First, the client redirects the resource owner to the authorization server with a request that includes the client ID, the requested scope, and a redirect URI. The authorization server authenticates the resource owner, usually by asking them to log in. Then it shows a consent screen with the requested permissions. If the user consents, the authorization server redirects back to the client with an authorization code. This authorization code is not the access token. It's a temporary code that proves the user consented. The client then makes a back-channel request to the authorization server, sending the authorization code along with a client secret. This client secret is a password that only the client and authorization server know. It proves the client is legitimate. The authorization server validates the code and the secret, and if everything checks out, it issues an access token. The client stores this token and uses it to call the resource server's API. Why the 2-step dance with the authorization code and then the access token? Security. The authorization code flows through the browser, which is a public channel. Anyone could intercept it. But the code alone is useless without the client's secret. The actual access token is exchanged over a secure back channel between the client server and the authorization server, never exposed to the browser. There are other OAuth flows for different scenarios. The implicit flow was designed for browser-based apps that can't keep secrets, but it's now considered insecure and deprecated. The client credentials flow is for server-to-server authentication, where there's no user involved, just 2 systems talking. The device flow is for devices without browsers, like smart TVs, where you enter a code on another device. And the newer authorization code with PKCE flow adds extra security for mobile and single-page apps. But here's the thing about OAuth. It tells you nothing about the user. An access token proves the client is authorized to access certain resources, but it doesn't tell you who the user is. For that, you need authentication. You need OpenID Connect. Press OpenID Connect authentication on top of OAuth. OpenID Connect, or OIDC, is a thin identity layer on top of OAuth 2.0. It adds authentication to OAuth's authorization. With OIDC, when the authorization server issues tokens, it issues two tokens, an access token and an ID token. The access token works the same as in OAuth. It's used to access APIs. The ID token is new, and it's specifically about identity. An ID token is a JSON Web Token, or JWT, containing claims about the authenticated user. It includes standard claims like SUB, which is a unique identifier for the user, ISS, which identifies who issued the token, AUD, which identifies who the token is intended for, and EXP, which is when the token expires. It also includes profile information like name, email, and picture if requested. The beauty of OIDC is that it standardizes authentication. Before OIDC, every identity provider had custom APIs for getting user info. With OIDC, it's standardized. You get an ID token, you validate it, you extract the claims, and you know who the user is. OIDC also defines standard flows that build on OAuth. The authorization code flow works the same, but now you get both an access token and an ID token. There's also the hybrid flow, which gives you some tokens immediately and others later, useful for complex scenarios. Let's talk about what's inside an ID token, because understanding JWTs is crucial. A JWT has three parts separated by dots: header, payload, and signature. The header describes the token type and the signing algorithm. It might say, this is a JWT signed with RSA SHA-256. The payload contains the claims, all the information about the user. The signature is a cryptographic signature of the header and payload using a secret key. Here's the critical part. The signature proves the token hasn't been tampered with and verifies who issued it. When your application receives an ID token, it checks the signature using the public key from the identity provider. If the signature is valid, you know the token is authentic. You can trust the claims inside. This is why JWTs are self-contained. You don't need to call back to the identity provider to validate every token. You just check the signature locally. This makes them extremely efficient for distributed systems, where you might have dozens of microservices all needing to verify user identity. However, there's a trade-off. Because JWTs are self-contained, you can't revoke them. If a user logs out, their JWT is still valid until it expires. That's why JWTs have short expiration times, often 15 minutes or an hour. You pair them with refresh tokens for longer sessions. A refresh token is a long-lived credential used to get new access tokens and ID tokens without making the user log in again. When your access token expires, your app sends the refresh token to the authorization server and gets a fresh access token. Refresh tokens can be revoked, so if a user logs out or their account is disabled, you revoke their refresh tokens and they can't get new access tokens. Policy-based authorization in practice. Now that we understand how users authenticate and how we get claims, let's talk about how to use those claims for authorization decisions. This is where policy-based authorization shines. In a claims-based system, you define policies as combinations of requirements. A requirement might be user must have claim role equals admin, or user must have claim department equals finance, or user must be over 18. Policies combine requirements with Boolean logic. In ASP.NET Core, for example, you might define a policy called Require Finance Manager that requires two claims, a role claim with value Manager and a department claim with value Finance. When a request comes in, the framework checks if the user's token contains both claims. If yes, access granted. If no, access denied. The power comes from separating the authorization logic from your business logic. Instead of sprinkling authorization checks throughout your code, you declare policies and attach them to controllers or endpoints. Your code stays clean, and your security logic is centralized and auditable. You can also build custom requirement handlers for complex scenarios. Maybe you need to check if a user is the owner of a resource, or if the user's IP address is in an allowed range, or if the user has accessed the resource within the last 30 days. You write a handler that implements your custom logic, and you plug it into the policy system. This is fundamentally different from RBAC. With RBAC, you're limited to the roles you've defined. With claims and policies, you have unlimited flexibility. You can make decisions based on any attribute, any combination of attributes, and even external factors like time or location. Sooner, token validation and security considerations. Let's dig deeper into how token validation actually works, because this is where many security vulnerabilities creep in. When your application receives a JWT, it must validate several things. First, the signature. You fetch the public key from the identity provider's JWKS endpoint, which is a JSON web key set containing the public keys used to sign tokens. You use this key to verify the signature. If the signature doesn't match, reject the token immediately. It's been tampered with or forged. Next, check the claims. Verify the issuer claim matches your expected identity provider. Verify the audience claim matches your application's identifier. Check the expiration time claim to ensure the token hasn't expired. Check the not before claim if present to ensure the token is valid now. You should also validate the token type. Make sure you're getting an ID token when you expect an ID token, not an access token. They have different purposes and different security properties. One common mistake is accepting tokens from unintended issuers. If your app is configured to accept tokens from https://login.microsoft.com, but someone sends you a token from https://evillogin.com, you'll reject it because the issuer doesn't match. Always validate the issuer. Another mistake is using access tokens for authentication. Access tokens are opaque to clients. They're meant to be sent to resource servers, not inspected by client applications. If you need to know who the user is, use the ID token. If you need to call an API on behalf of the user, use the access token. Token replay attacks are another concern. If an attacker steals a valid token, they can use it until it expires. This is why tokens have short lifespans and why HTTPS is non-negotiable. Always use TLS to encrypt tokens in transit, and consider adding additional protections like binding tokens to specific devices or IP addresses. Refresh token security is especially critical because refresh tokens are long-lived. Store them securely, never in local storage or cookies accessible to JavaScript. Use HTTP only, secure cookies or secure storage mechanisms provided by mobile platforms, and implement refresh token rotation. Every time a refresh token is used, issue a new one and invalidate the old one. This limits the window of opportunity if a token is stolen. Thus, Azure Active Directory and Entra ID integration. Let's bring this into the Azure ecosystem, because understanding how these concepts map to real cloud platforms is essential. Azure Active Directory, now rebranded as Microsoft Entra ID, is Microsoft's identity platform. It's an OIDC compliant identity provider that issues tokens for Azure resources and custom applications. When you register an application in Entra ID, you get a client ID and can generate a client secret. These are the credentials your app uses in the OAuth flows we discussed. You configure redirect URIs, which are the URLs Entra ID can redirect to after authentication. You define API permissions, which are the scopes your app needs. Entra ID supports all the standard OIDC flows. For web applications, you use authorization code flow. For single-page apps, you use authorization code with PKCE. For daemons and background services, you use client credentials flow. The token's Entra ID issues contain Microsoft-specific claims, in addition to standard OIDC claims. There's a tenant ID claim identifying which Entra tenant the user belongs to. There's an object ID uniquely identifying the user within the tenant. There are group claims listing the groups the user is a member of, though this can cause tokens to become large if a user is in many groups. One powerful feature is application roles. You define custom roles in your app registration, like admin or viewer, and assign users or groups to these roles in Entra ID. When a user authenticates, their token includes a roles claim listing their assigned roles. Your app checks this claim to make authorization decisions. For Azure resources like storage or Key Vault, Entra ID uses Azure RBAC. This is traditional role-based access control applied to Azure resources. You assign built-in roles like Storage Blob Data Reader or Key Vault Secrets User to users or managed identities. When code tries to access a resource, Azure checks if the identity has the required role. This is different from claims-based authorization in your application code. Azure RBAC controls access to Azure resources. Your application's authorization policies control access within your application. Often, you use both together. Azure RBAC to control who can access your database, and claims-based policies to control what operations users can perform in your app. Dafumon Workload Identity, service-to-service authentication in Kubernetes. In cloud-native applications running on Kubernetes, you often have services that need to authenticate to external systems like Azure Key Vault or databases. The traditional approach was to store credentials in Kubernetes secrets and inject them into pods. But this has problems. Secrets can leak, they're hard to rotate, and they don't integrate well with identity systems. Workload Identity solves this by giving Kubernetes pods managed identities in Entra ID. Here's how it works. You create a managed identity in Azure. This is an identity without a password, managed entirely by Azure. Then you create a Kubernetes service account and federate it with the managed identity using OIDC. The Kubernetes API server acts as an OIDC issuer, and Entra ID trusts tokens issued by your cluster. When your pod starts, Kubernetes injects a service account token. This token is a JWT signed by the Kubernetes API server. Your application code uses this token to request an Entra ID access token via a token exchange. It essentially says, "Here's my Kubernetes identity token. Please give me an Azure identity token." Entra ID validates the Kubernetes token, checks that it matches the federated credentials you configured, and issues an Azure Access token. Your pod uses this access token to authenticate to Azure services. No secrets, no passwords, just tokens all the way down. This is OAuth client credentials flow with a twist. Instead of using a client secret, you're using a Kubernetes-issued token as a client assertion to prove your identity. Workload Identity elegantly combines OIDC federation, managed identities, and Kubernetes service accounts to create a zero-secret authentication model for cloud-native apps. See now family real-world scenarios and design patterns. Let's walk through some real-world scenarios to see how all these pieces fit together. Scenario 1, multi-tenant SaaS application. You have customers, each customer has users, and users should only see data for their tenant. How do you model this? Use OIDC for authentication. When a user logs in, include a tenant ID claim in their token. In your application, extract the tenant ID from every request and use it to filter database queries. Implement a policy that requires the tenant ID claim to be present. For admin operations, require both a tenant ID claim and a role claim with value admin. This ensures admins can only administer their own tenant. For super admins who need to access all tenants, use a different claim or a different role. Never conflate regular tenant admins with platform-wide admins. And always log which tenant a user is operating in for audit purposes. Scenario 2, API gateway securing multiple back-end microservices. The gateway authenticates users, and back-end services need to trust requests from the gateway. The gateway validates the user's ID token and extracts claims. It then creates a new JWT, signs it with a key shared between the gateway and back-end services, and forwards this token to back-ends. The back-end services validate the signature using the shared key and trust the claims inside. Alternatively, use token propagation. The gateway forwards the original ID token to backends. Backends validate the token themselves using the identity provider's public keys. This avoids shared secrets but increases latency because every service validates tokens independently. You can mitigate this with caching. Scenario 3, mobile app calling a backend API. Mobile apps can't keep secrets, so client credentials flow is out. Use authorization code flow with PKCE. The app generates a random code verifier, hashes it to create a code challenge, and sends the challenge with the authorization request. When exchanging the authorization code for tokens, the app sends the original verifier. The authorization server validates that the verifier matches the challenge, proving the same app that started the flow is finishing it. This prevents authorization code interception attacks. Scenario 4, long-running background job that needs to access user resources. When the user initiates the job, your app requests an offline access scope. This grants a refresh token. Store the refresh token securely associated with the job. When the job runs, use the refresh token to get an access token and call APIs on behalf of the user. Handle cases where the refresh token is revoked, which means the user has revoked consent and the job should fail gracefully. Scenario 5, cascading API calls. User calls Service A. Service A calls Service B on behalf of the user. Service A uses the on behalf of flow. It sends the user's access token to the authorization server along with a request for a new token scoped to Service B. The authorization server validates the original token and issues a new token for Service B. Service A uses this new token to call Service B. This preserves the user's identity through the call chain and enables proper authorization and audit logging. Onwards, best practices and common pitfalls. Let's wrap up with best practices and pitfalls to avoid. First, use HTTPS everywhere. Tokens in transit must be encrypted. There are no exceptions. Second, keep tokens short-lived. Access tokens and ID tokens should expire quickly, ideally within an hour. Use refresh tokens for longer sessions and rotate them on every use. Third, validate everything. Check signatures, issuers, audiences, expiration times. Never trust a token without validating it. Fourth, minimize token size. Don't stuff every piece of user data into a token. Tokens are sent with every request, so large tokens increase bandwidth and latency. Include essential claims only and fetch additional data from a user info endpoint if needed. Fifth, secure refresh tokens like passwords. They're powerful credentials. Store them securely, never expose them to JavaScript, and revoke them when users log out. Sixth, use standard libraries and frameworks. Don't roll your own OAuth implementation. The spec is complex and full of edge cases. Use battle-tested libraries like Identity Server, Auth80, Okta, or cloud provider offerings like Entra ID. Seventh, separate authentication from authorization. Authentication tells you who the user is. Authorization tells you what they can do. Don't conflate them. Just because a user is authenticated doesn't mean they're authorized for every action. Eighth, design for failure. Tokens expire, networks fail, identity providers go down. Handle these gracefully. Provide clear error messages. Don't let users see cryptic 401 unauthorized errors without context. Ninth, audit everything. Log authentication events, authorization decisions, and token issuance. These logs are critical for security investigations and compliance. 10th, plan for token revocation. Even though JWTs can't be invalidated before expiration, you can maintain a revocation list and check it during validation. Or use reference tokens, which are opaque identifiers that require a back-channel call to validate. This adds latency but gives you real-time revocation. Common pitfalls: using access tokens for identity, accepting tokens from untrusted issuers, storing tokens insecurely, failing to validate token claims, making tokens too long-lived, exposing client secrets in public clients, and implementing custom crypto instead of using standard libraries. Conclusion: authorization and authentication are foundational to secure systems. RBAC is a starting point, but it's too rigid for modern applications. Claims-based identity gives you the flexibility to express complex authorization rules through composable attributes. OAuth 2.0 provides the framework for delegated authorization and token-based access. OpenID Connect adds standardized authentication on top of OAuth, giving you ID tokens with user claims. Together, they power the identity layer of modern cloud applications. Tokens, especially JWTs, are the currency of distributed systems. They're self-contained, verifiable, and efficient. But they require careful validation and security practices. In cloud platforms like Azure, these patterns come together through Entra ID, managed identities, and workload identity. You can build applications that authenticate users, authorize actions based on claims, and securely access cloud resources without ever managing credentials. The key is understanding the layered model: OIDC for authentication, OAUTH for authorization, claims for identity attributes, policies for authorization logic, and tokens for secure communication. Master these concepts, and you can design secure, scalable systems that meet real-world requirements. When you're in that interview and someone asks, "How would you implement authorization for a multi-tenant microservices architecture?" you'll know exactly where to start. Define your claims, design your policies, choose the right OAuth flow, validate your tokens, and build systems that are both secure and maintainable. That's the power of understanding these patterns deeply.